Okay, let's look at the work-energy theorem. This is an important theorem. This is an important definition for you to learn. It often comes up, and we always end up doing sums with the work-energy theorem. So the work-energy theorem says the work done on an object by the net force is equal to the change in kinetic energy of the object. So we know net work, that's that F delta x cos theta, okay? The net work is equal to the change in kinetic energy. So for instance, if you wanted to find the work done by brakes in a car, you could know the initial kinetic energy, you could know the final kinetic energy, and the change in energy is going to give you the net work. So there would be other ways to work it out with the displacement of the car, but you can work it out with kinetic energy. So these two formulas work hand in hand, okay? So the net work is equal to the change in kinetic energy. We know delta means final minus initial. So the net work is the final kinetic energy minus the initial kinetic energy. So we need to be flexible. Once we know the net work is equal to the change in kinetic energy, we need to be flexible in how we use the formulas. Okay, so the net work is equal to the change in kinetic energy. For work, we can substitute F net delta x cos theta, and because it's the net work, we use the net force. Okay, so the net work times the displacement times the cos of theta is going to equal to the change in kinetic energy, which is a half mv final squared minus a half mv initial squared. So the final velocity minus the initial velocity. Now a half is a constant and the mass is a constant, so we only need to worry about the final velocity. Sorry, I have to cough. So we only have to worry about the velocity here, okay? So the problem is it's the velocity squared. This is the safe formula to use, a half mv f squared minus a half mv I squared. This is the shortcut. If you use the shortcut, make sure you square the velocity, final velocity, and then subtract the initial velocity squared. You can't just put the squared outside the brackets or something random like that. Okay, so make sure if you're going to simplify it, you simplify it properly, or be safe and use these two formulas. Now we want to talk about forces. There's two kinds of forces, a conservative force and a non-conservative force. This conservative force has a random definition, and the definition's not that helpful to me in terms of explaining it. But let's have a look. A conservative force is a force exerted on an object moving on a closed path. The net work done by the force is 0. So what you need to take away from this, a conservative force is gravity or electrostatic forces. Okay, you can learn the definition, but you can think of them as gravity and electrostatic. So the main thing about this is the work done by a conservative force to get from A to B doesn't matter on the path followed. I'm going to show you with a non-conservative force what this path followed refers to. So it only depends on the end of the motion, okay? So a conservative force is also a force that allows the total kinetic energy to be converted into potential energy and back again. Can you see this part of the conservative makes more sense? Energy is being conserved. The force that allows the total kinetic energy to be converted into potential energy and then back into kinetic energy is called a conservative force. So conservative forces conserve energy. No energy is lost with conservative forces. On the other hand, non-conservative forces, and here's the definition, a force exerted on an object to do the work of moving it from A to B and back to A. It depends on the path taken. So non-conservative forces are friction, air resistance, and tension in a cord. This one comes up in questions quite often. This is not obvious, the tension in the cord, but it is a non-conservative force. So let's look at my people moving house here example. So look at the definition. A force exerted on an object to do the work of moving it from A to B and back to A depends on the path taken. If we want to get this couch from here to here, say we've just bought a new flat and we're moving in the furniture, and the wife is telling the husband where she wants the furniture and he's got to move the couch. If we move the couch from here to here, okay, and we're pushing the couch and there's friction. Friction is a non-conservative force. Think about it. If the wife says, take the couch from here to here, okay, perfect. But if the wife is like, let's think about this. Okay, the couch is over here. Oh, let's put it over there. And then she goes, oh, no, I can't see the TV. Okay, now put it over there. Okay, yes, we can keep it there. Which one of these had more energy? Okay, the path of this is going to remove more energy from the system. And if she's really indecisive and zigzags the couch all over the lounge before it ending up in the same place that this couch ended up, you can see that the more complicated the path, okay, the more energy is lost due to friction. So a non-conservative force depends on the path taken. So from here to here, not much energy is lost. From here to here to here to here to here to here, a lot of energy is lost. So remember the examples of all of these, because that's often the yes-no questions in the long answer questions. So non-conservative force is friction, air resistance, and tension in a cord. So with friction and air resistance, the potential energy is converted into kinetic energy and heat and sound, okay? So this means that energy is lost. Friction is always doing negative work, so it will always decrease the energy of the system. So whenever you look at a physics question, choose, is there friction or is there not friction? If there's friction, you cannot use the law of conservation of mechanical energy, because the friction is taking away the energy. So mechanical energy is not conserved when non-conservative forces are present. Okay, so mechanical energy will not be conserved. The total energy of the system remains the same, but the mechanical energy will not be conserved. Remember, the energy has disappeared off into heat and sound and all that other nonsense. Okay, so this is the law of conservation of mechanical energy expressed as an equation. If there's no friction and no air resistance and no tension, the potential energy and the kinetic energy added together at A will be equal to the sum of the potential and kinetic energy at B. Okay, you can't use this if there's friction. So if you have friction, the net work will be equal to the change in the kinetic energy. This is the original formula. But the work NC, and this NC stands for non-conservative, the non-conservative work will be equal to the change in kinetic energy plus the change in potential energy. So non-conservative work is always negative because friction is opposing motion. There's less mechanical energy because there's heat or sound or all those other byproducts. So this is the way you work out no friction, and this is the way you work out friction. Always remembering this delta EK, delta is the change in kinetic energy, change in potential energy. When do we use this? In pendulum problems, swinging backwards and forwards, roller coasters going up and down and up and down, and in free fall. So sometimes you can actually use these to solve vertical projectile motion questions. You'll sometimes see a work, energy, and power option in the memo, but I don't encourage it. Okay, if it's a closed or isolated system, you can use conservation of momentum as well in a closed or isolated system. So remember now, in these problems, you're going to have kinetic energy, so they've got a component of V in them. So like when we see an equation with a V in it, you're like, how can I find V? So one of the ways of finding V is using the equation of motion. But equations of motion are only for motion in a straight line. That's why you often see these questions are divided into curved surfaces and straight surfaces. If there's a curved surface, you may not use the equations of motion. If there's a straight surface, sometimes you can use the equations of motion. Then if you've got a pendulum problem, then the pendulum's swinging, it makes a circle, the motion's not in a straight line. So in pendulums, you have to use the energy equations. Okay, so if you want to find V, you use the energy equations for a pendulum. You can only use equations of motion if the motion is in a straight line. But of course, because physics is not straightforward, here we've got a pendulum which is making a circle. So we are going to use energy considerations. But this pendulum transfers energy to this block which moves in a straight line. And so boom, now all of a sudden you can use equations of motion. So you have to look sharp a little bit in these questions. Okay. So remember that, no equations of motion if the object is moving on a curved path.